morning, everybody, and welcome again to the CEIA Maths Tutorials Online. This morning's tutorial is differentiation and will be delivered by John Forrest. Okay, over to you, John.
Thanks, Eamon, and welcome, everybody. Okay, so good morning, everyone, and you're all very welcome. And as Eamon said, my name is John Forrest, and if following this class, if you have any questions, or you can email info@ceia.ie, and if you mention differentiation, any questions or feedback you have will get back to me. So this is my first online tutorial, and I've been thinking about this over the last couple of days. So I think there's advantages and disadvantages probably. We've certainly, some of us at least, if fewer time constraints, we don't have to be out of a lecture hall by a certain time, and people aren't relying on lifts or worried about parking tickets timing out and so on. And so we've a bit of flexibility. On the other hand, it's hard to get feedback. That I can't see anyone, so there's no body language. So I would encourage you to ask questions. You can do this immediately. There is I think there's a button on Zoom somewhere. Yes, if you click on the Q&A button, you'll be able to tap in any questions that you have, and Eamon will be able to communicate it to me, and I'll do my best to respond either immediately or else afterwards. So we have about 60 slides today, and all of them are numbered, so you can see how much progress we've made. And also, if you have a question, if you make a note of the slide number, that'll help me get back to it quickly. We are going to be working for about 2.5 hours this morning, and in the middle we'll take a break for a couple of minutes. And once the slides are completed, I can stay on afterwards if anyone's interested, and I do welcome any questions and feedback that you may have. And so you will need log tables, which are really, really important. You can't do differentiation without them. And a notepad, and if you have a math textbook to hand, you might find that useful as well. Okay, so we'll start. So I'm going to start off with a quick discussion about limits, because you need to understand a bit about limits before we actually get stuck into differentiation, the topic itself. So let's look at this function, x squared minus 1 over x minus 1. And this function at x, when x is equal to 1, this becomes 0 over 0. The function is not defined, and you can see in the graph there, you have this blue line, and then when x becomes 1, there's a what I'm calling a hole there, because the function is not defined at x equal to 1. And so we can allow x to get as close to 1 as we want, and also we can approach the number 1 from the left or the right. And we can see clearly that as x tends toward 1, f of x tends toward 2. And so we say the notation for this is the limit as x goes to 1 of f of x is equal to 2. More generally, we can say that the limit as x goes to L of f of x equals a as x approaches any limit value L. And just as a sidebar to that, you can't approach infinity, excuse me, because no matter how big you make x, it's still an infinite distance away from infinity. But we can make x as big as we like, and so we can state that in the limit as x tends toward infinity of f of x, that's a valid thing to say. The really important thing to know about limits is that when the limit exists, it is an exact precise value. The limit is not. It's not an approximation or an estimate. It is, and I think it's that's a question that's come up from time to time. Really important to understand that when you do find a limit of a function, that is a single and exact value. So this is a somewhat bit of a manufactured example, because the function that we started off with is x squared minus 1 over x minus 1. and we can factorize that. And so we can see that in this case, we see that the 2x minus 1s cancel. And so this really is just the function x plus 1. So you can see that it has an actual value and x is equal to 1. And in fact, there is a chapter in your book on limits, and one of the techniques that they use to help find limits for what you might call badly behaved functions is to factorize them. Okay, so now we can start talking about differentiation. So let's look at what differentiation does first of all. So differentiation examines functions, and it determines the rate of change of the output value y with respect to the input value x. And so here's a very simple function. It's a line, y is equal to 0.5x plus 2. And we know from the formula for the line that y is equal to mx plus c. We know that the slope is m. So this tells us that the rate of change of y with respect to x is m. So the slope in any function is equal to the rate of change, okay? But life starts getting a bit more complicated when we look at functions like these. So differentiation is the tool that we use to find the rate of changes of functions. So when we differentiate a function, we get a new function called f dash of x, or dy dx. F dash of x is a function derived from f of x. And so, and that function tells us the slope of f of x at every point on the curve. Excuse me. So a kind of an overview of what we're looking for then is we want a process where a function goes in, we do something to that function, and when it's done, the output of that process is a slope function, or a function that tells us what's the slope of the original function at every point. So the input is f of x, which is some function of x, and the output is f dash of x, also called dy dx. And that's a new function that tells us what the slope of f of x is for any given value of x. Since f dash of x is a function, we can differentiate that as well. And we will discuss this later in the second half, I think, of this presentation. So let's see how we go about doing this then. We want to find the slope of a curve, and of this curve C, we want to find the slope of this red curve, and we'd like to find the slope at A. And so our first guess might be to draw a line from A to B and say, right, that's approximately the slope of the curve at A. And so we might decide then, okay, well, that line from A to B is, yeah, it's okay, it's approximate, but we can do better. So let's pick a point that's closer to B, or that's closer to A, sorry, and this gives a better estimate. So here we've picked a point B dash, and we draw a new line from A to B dash, and you can see that's a better estimate. You can see the slope of the second line is closer to what the slope of the curve is at A. And so as we keep moving B dash towards A, the estimate gets closer and closer to the actual slope of the curve C at A. So how do we do this mathematically then? Well, let's take a look. This is a curve, and you can see the blue line is the curve, and we draw a line from x comma f of x up to the second point at x plus h, f of x plus h. So the slope of the line then becomes f of x plus h minus f of x all over h. So, and just highlight this distance here is h. And so when you've got at x, the value on the curve, or f of x, this point here on the curve is x comma f of x, and this point up here then is f of x plus h. is x plus h, comma f of x plus h. And so we can see from the that the slope of the line is f of x plus h minus f of x all over h. And so we want to find the slope as h gets smaller and smaller and smaller. We want to find the slope in the limit as h tends towards 0. And so, and this is how we write it down. So this is what we're looking for mathematically. We're looking for the limit as h goes to 0 of f of x plus h minus f of x all over h. And so I have a link to an animation for this here, which I hope I can get working. And so this shows graphically what we're doing. Okay, so here I've a slider button here, so you can see here h is equal to 2. And so what I want to do is I'm going to make h smaller and smaller and smaller. And if you watch the hypotenuse on the triangle, you can see that as h gets smaller and smaller and smaller, the slope of the hypotenuse gets much closer to the slope of the curve. Okay. So before we move on, let's talk about notation and language, because this topic of differentiation does introduce new notation. So we're saying the slope of f of x can be called dy dx. It can also be called f dash of x. And it's defined by the limit as h goes to 0 of f of x plus h minus f of x all over h. And this can be called dy dx or f dash of x, and it can also be called the derivative or the first derivative of y with respect to x. And that's because it's derived from f of x. The next thing to note is that dy dx, also known as f dash of x, it gives the slope of the tangent to f of x at x. And we will be coming back to that later. We'll be talking about tangents and how you find their slopes and so on. So if y then is equal to f of x, we can say dy dx is equal to f dash of x. If u is equal to g of x, then we can also say du dx is equal to g dash of x. So we don't really care if the variable is called y or u or x and so on. But generally speaking, we stick to y and x. So have we got anywhere, I wonder? Well, let's take a look. If you look at the limit as h goes to 0 of f of x plus h minus f of x all over h, well, if we let h go to 0, there's a risk that this becomes 0 over 0. So it's maybe it's worth trying a few examples and seeing how we get on with it. So here's an example. Let's let f of x be equal to 5x plus 3. And so then f of x plus h becomes 5 of x plus h plus 3. And so then f of x plus h minus f of x all over h, that becomes 5 into x plus h plus 3 minus 5x minus 3. And that becomes 5h all over h, and that becomes equal to 5. So we're saying that f dash of x is equal to 5. In this simple case, we didn't even have to evaluate the limit. So this looks like it might be useful. And so, but the question then is this result what we actually expected to see? And I think that the answer is yes, because f of x is equal to 5x plus 3. That's the equation of a line. And it's of the form y is equal to mx plus c. And here we see that m is equal to 5. And we also see that f dash of x is equal to 5. So this is returning the slope for the line, which is nice. Excuse me. So this is starting to look, starting to feel a little bit more optimistic now. We're seeing that in some cases we don't have to get the limit. We don't even have to get the limit, and it does seem to work pretty well. So let's try a more complicated example. What happens if f of x is a quadratic. So we've got f of x in this case now is 3x squared minus 5x plus 12. So f of x plus h is equal to 3 into x plus h squared minus 5 into x plus h plus 12. So I've colored that in red because you'll see it makes it a little bit easier to follow as we go down through the problem. So f of x plus h minus f of x all over h, that's equal to the red piece here, which is f of x plus h that we've already worked out, minus f of x, which is 3x squared minus 5x plus 12 all over h. And so when we work all that out, we square the x plus h piece here first of all. So that gives us 3 into x squared plus 2xh plus h squared. And then we work out the 5 into x plus h. So that's minus 5x minus 5h plus 12. And then we subtract the f of x here. So that gives us minus 3x squared plus 5x minus 12. And that's all over h. And so we multiply this out then, we get 3x squared plus 6x h plus 3h squared. And the rest of it is as it was before. And we can start cancelling then. So the x squareds cancel out, the 5x's cancel out, and the 12's cancel out. And so that leaves us with 6xh plus 3h squared minus 5h all over h. And that becomes 3h plus 6x minus 5. And now we do have to take the limit as h goes to 0. So in this case, the limit as h goes to 0 of 3h plus 6x minus 5 is equal to 6x minus 5. The 3h just vanishes, which is not bad. So dy dx is equal to f dash of x, and that's equal to 6x minus 5. Let's take a quick look and see can we visualize what's going on here. So just give me one moment here. So Desmos is a graphing calculator website that I use quite a bit, and I found it to be very useful and good. And I expect that there are many sites like this, and also there's some very good graphing apps that you can get for your phone as well, and they're often quite helpful when dealing with differentiation and also with other areas of maths as well. So I'm just going to type in 3x squared minus 5x plus 12. And we're going to zoom out a small bit here so you can see the graph there. And so if we're looking at the slope function for this, what are we expecting? Well, to the left of it, you can see that as you move further away, further to the left-hand side, you can see that the graph is initially, really, really steep. So the slope of it, we would be expecting to see a high negative value, okay? And then shortly after x is equal to 0, or we can see that the slope, it still is negative as we go down, but approximately as we get to the y-axis, we can see that the slope is turning around. It's still negative, but it's not as big a value. And then you see it turns, or the curve turns around here. And so you can see at some point the slope goes to 0. And then it starts climbing up again, initially fairly slowly, but within a short space of time, it's climbing up at a very rapid rate. So when we differentiated this, we got 6x minus 5. So let's take a look at that. So that blue line, that's the slope function for the original quadratic. And you can see it's that as you go further to the left, the line goes more and more negative. And that is, I think, pretty much what we would expect to see. And as we go to the right, we can see the line getting more and more positive. So that's just a quick visualization of what the kind of slope function looks like. And it is certainly worthwhile, I think I'd recommend that you spend a little bit of time doing exercises like this yourself and just getting a feel for, for many differentiation problems. It helps to be able to visualize, at least to some extent, what's going on. Okay, so that's that. So I'm going to leave here now. And we can move on to the next slide. So differentiation from first principles, it's interesting and it looks like it gives us the results that we need, but it's pretty laborious, especially for more complicated functions like, sine x or cos x or tan x or a to the power of x. So in order to save ourselves all of the hard work from having to differentiate these from first principles, we use rules. And on the logbook, I want to say it's page 25 on the logbook that I have. That's where all the rules for differentiation are. And I'd encourage you to keep that page open because we will be going through pretty much all of those rules over the next hour and a half or two. So let's start off and list out these rules and see what they mean and do some examples. Okay, so the first rule, if y is k times f of x, then dy dx is k times f dash of x, which is, so, and here's a very simple example. If y is equal to 15x, then dy dx is equal to 15. If y was 1x, dy dx would be 1. Okay. So the next item then is if we want to differentiate higher powers of n, so like y is equal to x to the power of n, then dy dx is equal to n times x to the power of n minus 1. And so, for example, if y is x to the power of a half, then dy dx becomes a half x to the power of minus a half. So you can see what we did there. It's n times x to the power of n minus 1. So n is a half. So that's where we get the half x from. And n minus 1 is minus a half. So that's where we get the minus a half from. And as an aside here, I would say that in doing differentiation, a knowledge of logs and powers and exponents is important. And we will touch on that again later. So from this rule, it follows that if y is equal to k, some constant, we can say that y is equal to kx to the power of 0, because x to the power of 0 is always 1. Okay, and then we can use this rule to differentiate it. And when we differentiate x to the power of 0, we get 0 times x to the power of minus 1, which is 0. So dy dx is always 0. So the derivative of a constant is always 0. And that is kind of, I think, again, not entirely unexpected, because if you draw a graph of a constant, say like y is equal to k, that's simply a horizontal line and it's got a slope of 0. So you can demonstrate this graphically, and you can also demonstrate this mathematically as well using this rule. So the sum rule is the next one, and here I'm going to say, when we say for these rules that y is equal to u plus v, we are saying that both u and v are functions of x. Okay, so what we're saying here is if you take two functions of x, and one is u of x and the other is v of x, and you add them, then when you differentiate, it's the same as you can add the two differentials just as you added the two functions. So here's an example. So y is equal to 7x cubed plus 3x squared. So we're adding two functions here, u and v, you could say. And dy dx, so let's differentiate the first one first. Dy dx is 7x cubed. And from our power rule here, when you differentiate x cubed, you get 3x squared. So when you differentiate 7x cubed, you get 21x squared. And again, with 3x squared, when you differentiate that, when you differentiate the x squared piece, you get 2x. And you multiply that by 3, and you get 6x. So now let's look at what happens when you multiply two functions together. So here, y is equal to u, v, where u and v are both functions of x. dy dx, the rule is u dv dx plus v du dx. And I do have some examples from that, but I can't fit them all on this slide. So I'm going to cover the rules in this slide and then do some more examples in a minute. We similarly have a quotient rule. That's where when y is equal to u over v, dy dx is equal to 1 over v squared into v du dx minus u dv dx. Again, if you have the logbook open, that rule is there, and we will be coming back to it. And then finally, the chain rule, and this is the function of a function rule. So if y is a function of u and u is a function of x, you can still find dy dx, and the way you do it is you get dy du and you multiply it by du dx. So these rules here, as written down, I think certainly may look a little bit puzzling at first, but once we get through a few examples, I think it'll all become clear. And so at the bottom, I'm just noting what I've said already: u, v, dy dx, dv dx, du dx. These are all functions. Y is a dependent variable, and rules can be combined. So when I say y is a dependent variable, y depends on the value of x. So x is what's called the independent variable. So you can move x, or you can change the value of x any way you want. And then when you apply the function f of x or u of x to x, and you get y, the value of y depends on the value of x. And also the other thing to note is that these rules can be combined. So for example, if you look at what I did here, when I said y is equal, I'm using two rules there. And the first rule is I'm using where k is a constant. So here 7 is the constant in the first part. So that's 7x cubed. And so we're saying when we differentiate it, it's 7 times the value of what you get when you differentiate x cubed. And obviously we're using to differentiate the x cubed piece here, we are using the x to the n rule up here. So already we've seen that we can combine more than one rule to get the result that we need. Okay, so here's an example of the product rule. So we're saying y is equal to, and the rule is y is equal to u multiplied by v, so dy dx is equal to u dv plus v du dx. And so here's our example then. We're saying f of x is 3x plus 4 multiplied by x minus 2. So I'm going to call 3x plus 4, I'm going to say is u, and x minus 2 I'm going to say is v. So f dash of x then, now let's look at what we're doing here. We're saying this is u dv dx. So but dv dx is equal to 1 because v is equal to x minus 2. And so when you differentiate that, when you differentiate x, you get 1, and minus 2 is a constant. So you get 0, okay? So when you what we're saying is when you differentiate the v piece, this is what you get, okay? And so what we are looking at down here then, this is u times dv dx, okay? And then for the second step, we want v times du dx. So we see that v is x minus 2. So we write down x minus 2, and we multiply that by du dx. And we see when we differentiate 3x plus 4, we get 3. And so that's where it comes from. And so you when you multiply these out, which is fairly simple, and you add, you get f dash of x is equal to 6x minus 2. So I hope that that everyone is able to follow this, and that it's making sense. And I don't know if we've any questions, or are people happy so far?
There's no questions at the moment, no open questions.
Okay, that's great. So let's carry on. And again, I would encourage people to do ask questions. This is a fairly complicated subject, and we're going through it quite quickly. So let's look now at the quotient rule. So for the quotient rule, this is the rule here. It's dy dx is equal to 1 over v squared into v du minus u dv dx. A little bit more complicated than the product rule, but still very doable, as we'll see. So let's say f of x is equal to 3x plus 2 all over x squared minus 3. So there we can see we're going to put, so u is 3x plus 2, so du dx is equal to 3. And v is x squared minus 3, so dv dx is equal to 2x. Okay, so f dash of x then, that's equal to v du dx. So we said that x squared minus 3 is equal to v, and du dx is equal to 3. So that's x squared minus 3 multiplied by 3. That's our first step. And then it's minus u dv dx. And so u is 3x plus 2, and we said dv dx is 2x. And so this is our minus our minus u dv dx piece. And under the line we have v squared, and that's x squared minus 3 all to be squared. And so when you multiply all that out, you get f dash of x is minus 3x squared minus 4x minus 9 all over x squared minus 3 all to be squared. That looks like it might be simplified a bit, but we kind of don't really mind at this stage, because our mission or our goal was just to differentiate the original function. And so now we move on to the chain rule. And so the rule again is a reminder: if y is a function of u of x, then dy dx is dy du multiplied by du dx. And I'm going to say that the chain rule is probably, to do differentiation, you need all of the rules, but the chain rule is the one that sort of stands out as being, really, really important. So let's look at this example. Y is equal to 3x plus 4 all to be squared. Okay, so here we can see that, u of x is 3x plus 4. And so du dx is equal to 3. And here we can see that y is u squared, so dy du is 2u. And so finally, we can say dy du by du dx is equal to, which is equal to dy dx, and you can see the dy du piece is in red and the du dx piece is in yellow, just to be able to follow it a bit more easily. So dy du is 2u, du dx is equal to 3, that's equal to 6u. But we've already said that u is equal to 3x plus 4. So we substitute the u back in here. And so we get 6 into 3x plus 4, and that's equal to 18x plus 24. Now we could, if we wanted to, we could have multiplied 3x plus 4 all to be squared. We could have multiplied it out and then differentiated that way. And it's actually so either way is valid, but for more complex functions, it's the chain rule is much more powerful in a lot of situations. Having said that, both approaches are valid, and it's nice to get the same answer each time, so that it gives you a way sometimes of being able to check your own work. But generally speaking, for more advanced problems, the chain rule is it's the best and possibly the only way to find a solution. Okay, so here's a second example of the chain rule, and we're starting to get into a little bit of real math now. So functions f and g are given by f of x is equal to 3x plus 1, and g of x is equal to x squared minus 2. So the first part of the problem is find p of x, where p of x is equal to f of g of x. The second part then is find q of x, where q of x is equal to g of f of x. And then the third part is differentiate p of x, differentiate q of x, set them equal to each other and solve for x. So let's see how we go. So p of x, first of all, is f of g of x. So that means it's 3 of g of x plus 1, because f of x is equal to 3x plus 1. And g of x is equal to x squared minus 2. So 3 times g of x plus 1, when you plug it in there, you get 3x squared minus 6 plus 1. So p of x is equal to 3x squared minus 5. Similarly, q of x is equal to g of f of x. And so g of x is x squared minus 2. So g of f of x is f of x squared minus 2. And so you then put in the value of f of x, which is 3x plus 1. So f of x squared minus 2 becomes 9x squared plus 6x plus 1, in brackets, minus 2. And that becomes 9x squared plus 6x minus 1. So solve p dash of x is equal to q dash of x. So we can, when we differentiate, 1 second, let me just get my highlighter up here again. So p dash of x, we can differentiate this just by looking at it. It's 3x squared minus 5. So when you differentiate, you get 6x, because minus 5 is a constant. And when you differentiate that, you get 0. And q dash of x, when you differentiate that, you differentiate the 9x squared piece first. That gives you 18x. Then you differentiate the 6x, and that gives you 6. And then you differentiate the minus 1, and you get 0. So q dash of x is equal to 18x plus 6. And so we can solve, and it's pretty easy to solve that to get x equal to minus a half. So there's an alternative way of doing this, and that's using the chain rule. So if we say that p of x is equal to f of g of x, and that in turn is 3g of x plus 1, as we had above, we can simply say straight away p dash of x is equal to df dg by dg dx. And df dg is 3, and dg dx is 2x. So that gives us 6x, as we had before. And the second piece then, q of x equal to g of f of x, which is equal to f of x squared minus 2. We can just say q dash of x is equal to dg df by df dx. That becomes 2 of f of x multiplied by 3. That becomes 6x plus 2 all multiplied by 3, and that becomes 18x plus 6. So we're getting the same result. And I think using the chain rule for this is, I think, is neater than doing it the first way. I think it's interesting to be able to compare the two ways of doing it. So here's another example, and this is again a little bit more complicated. So f of x is equal to the square root of x minus 1 all over x plus 1. So we find the value of f dash of x when x is equal to 5 over 4. So again, we're going to let u be equal to x minus 1 over x plus 1. Okay, so excuse me one moment. So y is equal to u to the power of a half, and dy du is equal to a half u to the power of minus a half using the power rule. And that's a half multiplied by 1 all over x minus 1 over x plus 1 to the power of a half. Okay, so we found dy du. Our next step is to find du dx. And for du dx, we use the quotient rule. And so we're saying, if you remember from the quotient rule, x plus 1 is equal to v, because that's under the line, and x minus 1 is equal to u, which is over the line. Now, just a little note here, we've already said that u is equal to x minus 1 over x plus 1, and that's correct. Down here, it's important to note that this is a different u. We are using this rule to differentiate x minus 1 over x plus 1. So we're kind of, in the context of this line, the u is the x minus 1 that's over the line. We're not cheating or anything. It's just a notation thing for convenience. We could call this 1 over p squared into p dq dx minus q dp dx or something here if we wanted to. So anyway, so it's from the quotient rule, we've got our 1 over v squared, so that's x plus 1 squared is under the line, and over the line we've got v du dx. So the du dx is equal to 1, and so v times du dx is simply x plus 1, and u dv dx then similarly becomes x minus 1, and so du dx works out as 2 all over x plus 1 to be squared. That's again using the quotient rule. So our third step then is dy dx is equal to dy du, which is in red, multiplied by du dx, which is in yellow. So that's the first piece here, the half by 1 over x minus 1 over x plus 1 to the power of a half, all multiplied by 2 all over x plus 1 to be squared. And so you can see that the 2 and the half cancel, and you get 1 all over x minus 1 over x plus 1 to the power of a half, all multiplied by 1 over x plus 1 to be squared. And that is our result. That's our differentiation done. To find f dash of 5 over 4 then, you just plug in 5 over 4, let x be equal to 5 over 4, and the result is 16 over 27. And so because we're concentrating on the differentiation aspect, and also because it's quite a long section, I tend to not go too deeply into the algebra, but you might want to make a note of that result for yourself and see if you can work it out. Later. So that's the basic sort of differentiation done, the product rule, the chain rule, and the quotient rule. And so now we're going to move on to what happens when you differentiate trigonometric functions like sine of x and cos of x and tan of x. So we've got more rules here. If f of x is sine x, f dash of x is equal to cos of x. If f of x is equal to cos of x, f dash of x is equal to sine of x. Sorry, it's equal to minus sine of x. And if f of x is equal to tan of x, f dash of x is equal to sec squared of x. And from the chain rule, if I'm just going to list these rules here, they are in your logbook, and I'm going to do a couple of examples rather than kind of getting stuck into rather than try to sort of explain verbally what they mean. Actually, these three rules here are not. They're not in the logbook that I have, but they're definitely in the textbook, and we'll be coming across those in a minute and doing some examples. So first of all, just a couple of notes. One is sec of x is equal to 1 over cos of x, and the other is we kind of don't care in many of these problems. We don't care too much about the properties of the actual functions themselves. So we don't need to be able to sketch sec of x or sec squared of x or any of that. We just care about differentiating them. And some of these problems can look a bit onerous. They can look a bit more complicated than they really are. But all you need is the rules, especially the chain rule, and some practice, and you'll be able to crack it, I think, without much difficulty. So let's try this first example. Y is equal to 10 to the power of 4 of 3x. So straight away, we can see this is, we can see we're going to need a trig rule to solve this, and we're also going to need the chain rule to solve this. So let's have a look. So y is equal to 10 of 3x. Let u be 10 to 10 of 3x. So y therefore is u to the power of 4. dy du is equal to 4u cubed, and that's 4 10 cubed of 3x. So that's our chain rule piece done. And we now need to find du dx, given that u is equal to 10 of 3x. So here we use the chain rule again. We note that if f of x, first of all, we note that if f of x is 10u, f dash of x is sec squared u multiplied by du dx. Okay, so du dx then becomes 3 sec squared 3x, because what we've done here is we've made another, we've used the chain rule again. Okay, so so we're saying let 10 of 3x be equal to 10 of u. So when you differentiate that, you get sec squared u. But then we also have to differentiate the 3x in here to get the du dx piece. And so that gives us, and that's where this 3 comes from. Okay, so and you can see again we're kind of using u's to mean slightly different things at different times, but it all works out. So dy du by du dx then becomes 4 10 cubed x from the first piece multiplied by 3 sec squared x, and that becomes 12 10 cubed x multiplied by sec squared 3x, or 12 10 cubed 3x multiplied by sec squared of 3x. So if you look what we've done, we've gone from differentiating, fairly simple functions like 5x squared plus 3x and so on, and now we have moved on to much more complicated functions already. So you can see these rules are really powerful and help you to get a lot done quickly. So but they do require a bit of practice. So here's another example. If y is equal to sine of x all over 1 plus tan of x, find f dash of 0. Okay, so f dash of x from the quotient rule, so it's u over v, so it's v squared under the line, and on the top line we've got v du dx minus u dv dx. So the v piece is 1 plus tan x. When you differentiate sine x, you get cos of x. So that's your v du piece. And then your u dv piece is sine of x is u. And when you differentiate 1 plus tan of x, you get sec squared of x. Okay. And so then f dash of 0 becomes 1 plus tan of 0, which is 0, multiplied by cos of x, and cos of x is 1. So this just becomes 1 plus 0, but sine of 0 is 0. So this part here vanishes. And so you get, you simply get 1 plus 0 multiplied by 1, and that is equal to 1. So what started off as a fairly complicated looking function, sine of x all over 1 plus tan of x, we were able to differentiate that in 2 lines, which is nice. So now we move on to inverse trig functions, and again, these rules are in the log tables. Yes, I have them open here in front of me. So so we just, again, there's rules for if you want to differentiate the arc sine of x over a. There's also if you want to differentiate the arc sine of u, where u is a function, the rules explain how to do all of that, and we'll be going through that in the next couple of slides. So here's the first example. So, and I'm saying f of x is equal to the arc sine of x over a, f dash of x is equal to 1 all over a squared minus x squared all to the power of a half. Is everyone familiar with the inverse trig functions? I think everyone has come across this before, that the sine minus 1, if you like, of 2x, which reads as arc sine of 2x. It's the opposite to getting the sine. So when we say y is equal to arc sine of 2x, what we mean is y is the angle which has a sine of 2x. Okay. So we let u be equal to 2x as we want to differentiate this. So du dx is equal to 2. And then y is the arc sine of u. So dy du is equal to 1 all over 1 minus u squared all to the power of a half. And that is from this rule up here. And then you just, you put in, we said that u is equal to 2x. So instead of 1 minus u squared here, we put in the 1 minus 2x all to be squared. And that gives us 1 minus 4x squared. And so that's our differentiation done. Okay. And so dy dx, which is equal to dy du by du dx, is 2 all over 1 minus 4x squared all to the power of a half. Okay, so let's move on to the next example. And this example is, it's the same one, only quicker. Okay, and we'll see what we mean. So back here, we just said if f of x is equal to the arc sine of x over a, right? Now we're doing the chain rule version of this. So we're saying the rule here now is if f of x is equal to the arc sine of u, f dash of x is equal to du dx multiplied by 1 over 1 minus u squared all to the power of a half. Okay. And so we're now looking at y is the arc sine of 2x. And so f dash of x, and we can just write this down straight away. We can say, right, we can see straight away that u is equal to 2x. So the du dx is equal to 2. And then it's just, you just substitute, you put in 2x for u here, and you get 1 over 1 minus u squared all to the power of a half. And bang, you're done. So, sorry, let me, whoops. So you can see we were able to solve this in one single line just by using the chain rule version of the arc sine rule. Whereas in the previous example, it took us 2 or 3 lines to get there. So I would urge you, we don't have time today to go through a huge number of examples, unfortunately, but I would definitely recommend that you practice some of these. They all look a bit more complicated than they actually are, and honestly, with practice, you will find that you will be able to differentiate functions like this in 1 or 2 lines without any difficulty. So here's a more advanced example then. So, and the rule here that we're going to use is if f of x is equal to the arc tan of u, f dash of x is equal to du dx multiplied by 1 over 1 plus u squared. For this example, we also need to know that the sine pi over 6 is a half and cos pi over 6 is root 3 over 2. And so the question then is, why is the arc tan of cos of x? Find f dash of pi over 6. And so u is cos of x. So the du dx is minus sine of x. And 1 over 1 plus u squared is 1 plus cos squared of x. And so that's our differentiation done in one single step. And so we can now evaluate it, because we need to find what is the value of f dash of x when x is equal to pi over 6. So minus sine of pi over 6 is minus a half, and the cos of pi over 6 is root 3 over 2, and so cos squared of pi over 6 is 3 over 4, And so this all becomes -1/2 multiplied by 1 all over 1 plus 3 over 4. And that becomes -1/2 multiplied by 4 over 7. And that becomes -2 over 7. Some of you, I'm going to leave this up here for a second. Some of you might want to make a quick note of it, especially if you're gone a bit rusty with algebra. And again, if you want to, you can just make a note of the answer and how we got there, and maybe practice later then yourself. Okay, let's move on. So at this point, we've covered the product rule, the quotient rule, the chain rule. We've done trigonometry. And now we're going to take a quick look at second derivatives. This is where you differentiate a function twice, okay? So we know that when we differentiate a function f of x, we get f dash of x. F dash of x is also a function, so we can differentiate that too to get f double dash of x, okay? And so the notation that we use, y is equal to f of x, dy dx is equal to f dash of x, and what we call d2y dx squared is equal to f double dash of x, and so on. You can keep differentiating, you know, until you, if it's a polynomial, you'll eventually, if you differentiate it enough, you'll end up at 0. But for example, you couldn't differentiate sine of x and cos of x all day long, and so you can get f triple dash, f4 dash, f5 dash, and so on. One thing to be aware of, though, is that d2y dx squared is not at all the same as dy dx all to be squared. Okay, it's an easy mistake to make, and especially when we call when we say d2y dx squared, the piece under the line, it sounds like we're squaring it, but we're not. It's just it's a figure of speech, really. So, and here's an example. If y is equal to x cubed, dy dx is equal to 3x squared, and d2y dx squared is equal to 6x, but dy dx, all to be squared, is 9x to the power of 4. So they're two different outcomes entirely. So that's something to be aware of. Okay, and let's move on. So we're now going to look at the equation of a tangent. So the problem here is a well-known kind of maths problem called the tangent problem, which is you're given a curve and you're given a point in a curve, and the problem that you need to solve is, how do you find the equation of the tangent that touches the curve at that point? So here are the steps that we do. You first, to find the equation of a tangent to a curve, the first thing you do is you find an expression for dy dx. Then you evaluate dy dx and y1 at the desired point, because we're saying we want to find the equation of a tangent to a curve at a specific point on the curve. So you evaluate dy dx and you evaluate y1 at the desired point, and then the equation for the line then becomes y minus y1 is equal to m into x minus x1, where m is equal to dy dx. Okay, so I think reasonably straightforward process here. And so let's do an example. Find the equation of the tangent to y is equal to arc tan of x at x equal to 0. Okay, and I'm just put in a reminder. If f of x is equal to the arc tan of x over a, then f dash of x is equal to a over a squared plus x squared. So if f of x is equal to the arc tan of x, f dash of x is equal to 1 all over 1 plus x squared. So that's the differentiation piece done. And f dash of 0 is equal to 1, because we want the slope of the tangent at when x is equal to 0. So the slope is 1. And also we know that if y is arc tan of x, when x is equal to 0, y is equal to 0. And so this becomes fairly simple. We want to find the equation of a line with slope 1 passing through the origin, and the answer is y is equal to x. So that's a pretty straightforward example. Let's move on. So find the equation of the tangent to the curve. No, I've actually made a mistake here because we haven't covered exponentials yet. I'm going to make a note here, and I'm going to come back to this one on slide 32. And I'll do that after the break, which is coming up shortly. So let's just look at question 2 here. The slope of a tangent to y, which is equal to x to the power of 4 minus 1. The slope of it at some point p is 32. Find p. So here we're saying very quickly, f dash of x is equal to 4x cubed. 4x cubed is equal to 32. X cubed is equal to 8. And so x is equal to 2. And so the point then is 2 comma 15, because if you let x be equal to 2, x to the power of 4 is 16, and you subtract 1 and you get 15. Okay. So we're coming up to a break now. So I've just a couple of questions. And so the first one is, why is the derivative of a constant equal to 0? The next one is, there anything that we cannot differentiate? And the next one is, can sine of x be expressed as a polynomial? Why or why not? And just a quick reminder on what a polynomial is. It's an expression with a finite number of terms, and you're allowed to use constants, variables, and powers combined using addition, subtraction, multiplication, and division. So here's a simple example of a polynomial. And so right now we're going to take a break. I'm going to leave this slide up, and it is now 11:05. So I expect to be back in about I'm about 6-7 minutes, something like that. Let's say yeah, it's just 6 minutes past 11 now. We'll be back in about 5 minutes. Thanks.
Okay, folks, see you back here in about 5 minutes. That would be just after about 11:10. So please be back here for then.
So let's move on again. So one of the questions that we asked was, is there anything that we cannot differentiate? So here's a very simple function. This is y is equal to the absolute value of x. And so for those who are not familiar with that function, y is equal to x when x is positive, and y is equal to minus x when x is negative. And the question then is, what is dy dx when x is equal to 0? And the answer is, it's not differentiable at x equal to 0. And the reason for that is that we do not know the slope of the tangent to this function when x is equal to 0. So I'm going to, like this line here, this line is a bit terrible, but because I'm just using my mouse. Anyway, if you imagine that's a straight line, that's one possible tangent to the curve. And this line here is another possible tangent. The mouse isn't a great implement for trying to draw with, but I think you get the idea. So not everything is differentiable, which most of the time that's not going to bother us, but at the same time it's good to know. And so the next one then is, can sine of x be expressed as a polynomial? Well, what happens if you differentiate this? So this is a general polynomial, looks like this: a constant term, then some term in x, and some term in x squared, and some term in x cubed, all the way up to x to the power of n. And when you differentiate that, okay, f dash of x, so the constant term vanishes. So you get 0 plus a1 plus 2a2 times x plus 3a3x squared, and so on and so forth. And so you can see we started off with a polynomial where the highest power of x is n. Now the highest power of x is n minus 1. And so if you keep differentiating, the polynomial will eventually vanish. It will eventually go to 0. Okay. But if you keep differentiating sine of x, cos of x, tan of x, and e to the x, and we'll talk about e to the x in a minute, you can keep differentiating those functions indefinitely. Sorry. So that would suggest that sine of x cannot be expressed as a polynomial, and that is true. It can't be expressed as a finite polynomial. So that was just a couple of questions to, for you to think about over the break. Okay, so let's move on then. And so you will now need to, for the next, for this part of the presentation, you will need to know the rules of logs, and that I believe is also in your logbook. And I think it's on page 21. So it would be good to have, yeah, page 21 indeed has lots of rules about indices and logarithms. So that might be a handy page for you to be able to refer to as we go forward. And so I'm not going to go in any depth in here because I just wanted to put these rules up just to remind you, because we will be using them shortly. And so now we move on to differentiation of exponentials. So exponentials are functions that are related to e to the power of x. So the rules here then are, if y is equal to e to the power of x, then dy dx is also e to the power of x. This makes e to the power of x a very important function, and in fact that function comes up over and over in any mathematics to do with engineering, or things like rates of chemical reactions or growths of populations and statistics. E to the x turns up in all sorts of weird and wonderful places, and it's one of the most important functions in math. If y is the natural log of x, and I'd remind everybody that the natural log is the log to the base e of x, then dy dx is equal to 1 over x. And if y is e to the power of some function of x, then dy dx is equal to f dash of x by e to the power of f of x. And that's simply the chain rule. And if y is the natural log of some function of x, then dy dx is f dash of x over f of x. And that is the chain rule again. So let's look at some chain rule examples with exponentials. Let's differentiate y is equal to the natural log of f of x. So we let u be equal to f of x. So y is the natural log of u, and dy du is equal to 1 over u. And also du dx is equal to f dash of x. And so therefore, dy du by du dx is 1 over u multiplied by du dx, and that's 1 over f of x multiplied by f dash of x, as we have already seen. So this just simple chain rule example to explain where that particular rule comes from. So dy dx is equal to f dash of x over f of x, as we have already seen. So, and an exercise for yourselves then is, if y is equal to f of x, can you show that dy dx is equal to f dash of x multiplied by e to the power of f of x? And so I'll leave that up for a couple of seconds if you want to write that down and make a note of it and try it later on yourself. Okay, let's move on. Here's another example. If y is equal to x to the power of n, find dy dx without using the power rule. Okay. So x is equal to e to the power of the natural log of x. And so you do need to know your rules of logs to be able to solve this problem. Anyway, if x is equal to e to the power of the natural log of x, which it is by definition, then x to the power of n is equal to e to the power of n times the natural log of x. And so dy dx is equal to f dash of n times the natural log of x multiplied by e to the power of n times the natural log of x, and that's from the rule, because the rule says dy dx is f dash of x by e to the power of f of x. And f dash of n times the natural log of x itself, that is equal to n over x, because when you differentiate the natural log of x, you get 1 over x. When you multiply it by n, you get n over x. So dy dx is equal to n over x times e to the power of n times the natural log of x. And that is equal to n over x times x to the power of n, because we've already said that x to the power of n is equal to e to the power of n times the natural log of x. And n over x times x to the power of n, that's equal to n times x to the power of n minus 1, as we already know and as we already expected. And so I chose this example because it's a good example of using the chain rule with exponentials, and also it ties in with one of the rules that we know already. So here's another example of the chain rule that shows just how powerful it can be. Let's look at this. Y is equal to a to the power of x. There is a rule for this. I think the rule is not on the course, but we will go through this quickly anyway, because I think it gives better insight into what the chain rule can do. And it's quick. So let's differentiate. So let's start off with y is equal to a to the power of x. So the natural log of y then is equal to x times the natural log of a. So all we've done here is we've taken the natural log of both sides, okay? And now we can say, let u be equal to the natural log of y, which is equal to x times the natural log of a. Now u is a function in x, y is a function in x, and x times the natural log of a is a function of x. So we can differentiate. Du dy is equal to 1 over y, and du dx becomes the natural log of a. Okay, and that's from the product rule. But the chain rule tells us that du dy by dy dx is equal to du dx. Now here we have du dy and we have du dx, so we can find dy dx very simply. So 1 over y, which is du dy multiplied by dy dx, is equal to the natural log of a, and therefore dy dx is equal to y times the natural log of a. But we said y is equal to a to the x, so y times the natural log of a is equal to a to the power of x times the natural log of a. So you see what we did there. We found we don't know what dy dx is, but we were able to find du dy and du dx, and then figure out dy dx from that. And that's a nice way to be able to use the chain rule, and it's a nice tool to have in your back pocket in case you need it. So here are some more examples then. If y is equal to e to the power of 4 times tan x, then dy dx is 4 sec squared x multiplied by e to the power of 4 tan x, because remember the rule, this is e to the power of f of x, so dy dx is f dash of x times e to the power of f of x. And so f dash of 4 tan x is 4 sec squared x. And so that's why dy dx is 4 sec squared x by e to the power of 4 tan x. What about y then, if y is equal to the natural log of 1 over e to the power of x? So remember, dy dx this time around, it's f dash of x all over f of x. So dy dx becomes minus e to the power of minus x all over 1 over e to the power of x, because 1 over e to the power of x is equal to e to the power of minus x. Okay, so dy dx is minus e to the power of minus x, that's the f dash of x piece here, all over 1 over e to the power of x, that's the f of x piece here, and that becomes equal to minus 1. Now we could do this more simply if we noted that the natural log of 1 over e to the power of x is equal to minus x. So dy dx is equal to -1. But again, it's nice to take, I think, with starting off with examples, take fairly simple ones first and ones that you can solve in a different way so that you can reassure yourself that you're on the right track. Okay, so that's the exponential differentiation piece. And I did say we would go back to slide 32 because there was a tangent question there, 33, 32. So yeah, I made a slight mistake in putting this slide pack together. I had the slides arranged in a different order originally, but then I got some feedback and I changed the order, but I'd forgotten that I had an exponential question here. So the question here is find the equation of the tangent to the curve y is equal to x plus e to the power of 2x when x is equal to 0. So f dash of x becomes 1 plus 2 times e to the power of 2x. Okay, I hope everyone is happy with that. When you differentiate x, you get 1. When you differentiate e to the power of 2x, then you get that's e to the power of f of x. So f dash of x then is 2, and so you get 2e to the power of 2x. And so f of 0 is equal to 1, because when x is equal to 0, y becomes 1 because the x is 0, obviously, and e to the power of 0 is equal to 1. So f of 0 is equal to 1, and f dash of 0 is equal to 3, which is 1 plus 2. And so the point then, when x is equal to 0, y is equal to 1, so the point is 0, 1. The slope is 3, and so the line becomes y is equal to 3x plus 1. Okay, so let me fast forward again to where we left off. So yes, so we're going to talk about curves and certain landmarks that are on a curve. Okay, so here's a curve, and there are certain points on a curve that we have names for. So so looking here, we've got a local maximum. What does that mean? It means the curve has been steadily increasing in value until we get to this point, and then the curve starts to decrease again. Okay, and so a local maximum is not the maximum value of the curve, but it's the maximum value in, if you like, in some locality. So like, just bear with me now one moment. I made a bit of a boo-boo there. Let me try this again. Apologies for this now. I pressed the wrong button. Let me get back to where I was. I think it was here. Here, yeah. Okay. Slide. So the local maximum, you can see it's what it means is just in this locality approximately, it's the maximum value of the curve. And then you've got a local minimum, which is again in this locality roughly, it's a minimum value of the curve. And somewhere between the local maximum and the local minimum, what happens is between the local maximum and the local minimum, the curve initially starts to slope downwards. And so the curve starts going down and down and down, and then the slope gets a little bit less steep until you get to the local minimum where the slope again is 0. Okay, and so that point where that kind of point between the local maximum and the local minimum, where the curve, where the rate of change in the slope of the curve is 0, that is an inflection point. So what has all this to do with differentiation? Well, at a local maximum point, you have f dash of x is equal to 0, and also f double dash of x is less than 0. So you can see, let's talk about the f double dash of x piece. We know f dash of x is the slope. F double dash talks about what the rate of change of the slope, and you can see that if as we approach the initially down here, the slope is some very high positive value, and it's rising quite steeply. So f double dash of x, f dash of x is positive, but you can see that the slope gradually eases off until at the local maximum point, f dash of x is equal to 0. And so because the slope has been decreasing, f double dash of x all along this red area that I've highlighted is less than 0 everywhere. Okay, so at a local minimum point, using similar logic, f dash of x is equal to 0, but f double dash of x is greater than 0. And at the point of inflection, we don't care what f dash of x is, but we know that at the point of inflection, f double dash of x is equal to 0. And finally, you can have a saddle point, which is a special case of the inflection point where f dash of x is equal to 0 and f double dash of x is also equal to 0. And you might want to make a note of those, and we'll move forward then. Okay. So here's another curve showing some other examples. So you can see that we have got a local maximums here and here. We have a local minimum, and we also have a saddle point. And you can see that that is a point of inflection which is horizontal. Okay, and so at the saddle point, f dash of x is equal to 0, and f double dash of x is also equal to 0. Local maximum and minimum points can also be called stationary points or turning points. So you'll see in various problems in the textbook, sometimes they'll talk about a local maximum, sometimes they'll talk about a local minimum, and sometimes they'll talk about stationary or turning points. So it's important to have that language and know what those words mean. So we're now going to move on to a part of differentiation, which is to do with optimization. And optimization is about understanding the behavior of curves at these key points. And it's important. So optimization then is about finding the turning points. And I think the easiest way to explain it is to come up with an example. So first of all, let's find the turning points and state if they're local maximum or minimum points for this fairly simple equation. F of x is equal to x squared minus 2x plus 5. F dash of x is equal to 2x minus 2. And so f dash of 1 then is equal to 0. So because f dash of 1 is equal to 0, we know we have a turning point at 1, 4, because 1 squared minus 2 plus 5 is equal to 4. But we don't know if it's a maximum point or a minimum point. So we differentiate again. F double dash of x is equal to 2. F double dash of x is always positive. So the point 1, 4 is a local minimum. So here's another example then, a little bit more complex this time. F of x is equal to 1 minus the natural log of x, all to be squared. And we want, and x is greater than 0. Okay. So we use the chain rule again. Let u be equal to 1 minus the natural log of x. So y is equal to u squared. dy du by du dx is equal to 2u multiplied by minus 1 over x. And that's equal to minus 2 over x into 1 minus the natural log of x. And so this is 0 when the natural log of x is equal to 1. So x, therefore, if the natural log of x is equal to 1, x has to be e to the 1, which is e. And so again, I'd remind you that understanding of logs and exponentials in general is important here. So if we differentiate again, because we have found the local, we have found when we found the point where the function is equal to 0, or where f dash of x is equal to 0, but we need to differentiate again to figure out, is this a local maximum or a local minimum? And so we need to differentiate the highlighted piece in yellow there, and we're just making a note that 2 over x is equal to 2 to the power of x, or sorry, is equal to 2x to the power of -1. And so -2, so this becomes, using the product rule, we get -2 over x multiplied by -1 over x, plus 2 to the power of x minus 2, 2x to the power of -2 rather, into 1 minus the natural log of x. And so when x is equal to e, the natural log of x is equal to 1. So the second part vanishes, the part that's highlighted in that orange color there. And so we're then left with -2 over x by -1 over x. And that, when x is equal to e, that's 2 over e squared. This is positive, so E0 is a local minimum. Okay, so here's a few more examples of turning points. The curve y is equal to e to the power of x into px squared plus q. That curve is a local minimum at 1, -4e. Find the value of p and the value of q. So this is a slightly different twist on it. Here we're given the point, we're told it's a local minimum, and we just need to solve for p and q. So dy dx is, again using the product rule, it's e to the power of x into 2px, and q vanishes because it's a constant. And then it's plus px squared plus q times e to the x. So that's u dv dx plus v du dx. And that's equal to e to the power of x into px squared plus 2px plus q. And so this is 0 when x is equal to 1, because it's 0 because f dash of x is 0 at a local minimum. So when x is equal to 1, we can see that 3p plus q has to be equal to 0, because when x is equal to 1, you get p plus 2p plus q. So 3p plus q is equal to 0. Also, when x is equal to 1, e to the power of x into px squared plus q is equal to -4e. And we know this because we were told that the point, the y value, is -4e. And so if e to the power of x is equal to, into px squared plus q is equal to -4e, that means that p plus q has to be equal to -4, because x is equal to 1. So we combine 1 and 2 above. It's a simple simultaneous equation, and we find that p is equal to 1 and q is equal to -6. Okay, so now, something broke here. Yeah, so this will be sorry, apologies for this, a little bit confusing. Here's another example, f of x. So ignore what's in the bottom right hand corner here for a moment. I got this slide, I made a mistake setting up this slide. So the problem is f of x is equal to e to the power of 2x minus ae to the power of x. Show that f of x has a local minimum and find its coordinates in terms of a. Okay, so f dash of x is 2e to the power of 2x minus ae to the power of x. We know that from our exponential differentiation. So f dash of x is equal to 0 when 2e to the power of x is equal to a. Okay, and I hope everyone understands that. So 2e to the power of x is equal to a, and that implies that e to the power of x is equal to a over 2, and so x is equal to the natural log of a over 2. So f dash of x is equal to 0 when x is equal to the natural log of a over 2. When x is equal to the natural log of a over 2, f dash of x is equal to 2e to the power of twice the natural log of a over 2 minus a times e to the power of the natural log of a over 2. And so that becomes 2a squared over 4 minus a squared over 2 is equal to 0. And so f double dash of x then, we add up here, we have f dash of x is equal to 2e to the power of 2x minus ae to the power of x. F double dash of x is 4e to the power of 2x minus ae to the power of x again. So when x is the natural log of a over 2, f double dash of x is equal to 4e to the power of twice the natural log of a over 2 minus ae times the natural log of a over 2. And that becomes 4a squared over 4 minus a squared over 2, and that is greater than 0. So f double dash of x is greater than 0 implies that when x is equal to the natural log of a over 2, it is a local minimum. So the coordinates are natural log of a over 2 and f of the natural log of a over 2. And so sorry, this slide is a little bit out of sequence. I just, for this line here, I wanted to remind you all that e to the power of natural log of p is always equal to p. And that's where, that's how I was able to do the math in these lines here. So we've our differentiation done, and we now need to find the y value when x is equal to the natural log of a over 2. So we remember that f of x is equal to e to the power of 2x minus ae to the power of x. So f of the natural log of a over 2 is equal to e to the power of twice the natural log of a over 2 minus ae times the natural log of a over 2. And that becomes a squared over 4 minus a squared over 2. So the coordinates then are natural log of a over 2 and minus a squared over 4. And so apologies again, this slide is a little bit out of sequence, but I hope you've been able to follow the progress as we've solved this problem. Okay, so we now move on to optimization, which I mentioned a little bit before when we were talking about points of inflection and local maximum and minimum points and so on. So let's talk a little bit about optimization first. Optimization problems are concerned with maximizing or minimizing some value given certain constraints. So here's an example. A piece of wire 32 centimeters long is bent into the shape of a rectangle. So that for the rectangle to have maximum area, the rectangle will be a square. So in terms of optimization, usually with optimization, you have some kind of a constraint and you have some kind of outcome that you want to maximize. So in this case, the constraint is the length of the wire. We just have 32 centimeters of wire and we can't get any more. And we want to maximize the area of the rectangle, okay? So on the next slide, we'll go through, let's try the general case, okay? So here, a piece of wire of length P. So we're just saying it's not 32 centimeters, it's of some length P. So a piece of wire of length P is bent into the shape of a rectangle. Show that for the rectangle to have a maximum area, it has to be a square. So with many of these problems, it's helpful to draw a sketch first. And so here's our rectangle, and I'm calling the long side X and the short side Y, okay? And so the area is XY. So A varies with X, and we want to find dA dx. We'll come to that in a minute. Now the perimeter, P, that's 2x plus 2y, and P is a constant, it's the constraint. So the first thing that we want to do, the first thing that we want to do here is express the area totally in terms of X. So we note that P is equal to 2x plus 2y, so y is equal to P minus 2x all over 2. And area is equal to xy, So that's equal to x multiplied by px, it's equal to x multiplied by p minus 2x over 2. And so the area is px minus 2x squared all over 2. And so you can see what we did there. We've expressed the area in terms of x alone. Okay, so our next step then is to find dA dx and then find the value for x when dA dx is equal to 0. Okay, so dA dx we can see from up here. If we differentiate up here, a is equal to px minus 2x squared all over 2. So when you differentiate that, you get p minus 4x all over 2, and that becomes p over 2 minus 2x. And so we want to set that to 0. dA dx is equal to 0 when 2x is equal to p over 2, or in other words, when x is equal to p over 4. And so we'll continue our work here on the right-hand side. If x is equal to p over 4, then p is equal to p over 2 plus 2y. So y also has to be equal to p over 4. Because we remember we said that back here, and I try and use a different color. So we said over here, p is equal to 2x plus 2y. So if x is equal to p over 4, then 2x is p over 2. And so so from this, we can see that y is also p over 4. But if x is equal to p over 4 and y is equal to p over 4, that means it's a square. So that's a nice simple example of how we perform optimization using differentiation. So finally, we have to we know that dA dx is equal to p over 2 minus 2x. d2a dx squared is equal to minus 2. So by getting the second derivative here, we have proven that it's a local maximum. So here's another example of an optimization question. And this diagram, the diagram shows a cone with a base radius of 4 centimeters and a perpendicular height of 12 centimeters, and a cylinder of radius r and perpendicular height h stands inside the cone, such that the cylinder touches the curved surface of the cone. The cylinder has a volume of v centimeters cubed. And so the question then is, find an expression for h in terms of r, then find an expression of volume in terms of r, and then find the maximum value of volume, or of the volume of the cylinder. Okay. So on the next slide, I'm going to draw a slightly different picture of the cylinder. What I'm going to do is I'm going to cut the cylinder in half, or cut the cone and the cylinder in half, and show you a cross section. Excuse me. So let's look at a cross section. So we know that the entire cone is 12 centimeters high and the base is 4 centimeters in radius. And we can see the outline of the cylinder inside in the cone here. I'm just going to draw that in yellow. So you can see this is the outline of the cylinder, and the cylinder is of height h. And so you can see that the yellow triangle and the red triangles and the red triangle, they're both similar. So we know that h over 12 has to be equal to 4 minus r over 4. And I hope everyone can see where the 4 minus r came from here. The radius of the base along here, that's 4. The radius of the cylinder is r, so the base of the red triangle is 4 minus r centimeters. Excuse me. Oh, it's done this thing again. Sorry, guys. So this is the first part of the question answered. h over 12 is equal to 4 minus r over 4, and so therefore h is equal to 12 minus 3r. So that's our first step. So now we want to find the volume. So the volume of a cylinder is pi r squared h, and we know that h is equal to 12 minus 3r. So the volume then is pi r squared into 12 minus 3r. That's 12 pi r squared minus 3 pi r cubed. And so that's the second part of our question done, I think. So now we want to find the maximum value of the volume of the cylinder. So we evaluate dV/dr. And so dV/dr is equal to 24 pi r minus 9 pi r squared. And also d2V/dr squared is 24 pi minus 18 pi r. So we now want to find when dV/dr is equal to 0. So when dV/dr is equal to 0, then 24r is equal to 9r squared. So 9r is equal to 24. So r is equal to 8 over 3. So when r is equal to 8 over 3, that's when dV/dr is equal to 0. And now we differentiate again to prove that this is a local maximum value. Okay. So when r is equal to 8 over 3, d2V/dr squared is equal to 24 pi minus 18 pi r. And that's equal to pi into 24 minus 48, which is always less than 0. And so now, so we know we have a local maximum. Finally, when r is equal to 8 over 3, v is equal to 12 pi r squared minus 3 pi r cubed. And that works out at 256 pi all over 9. So the maximum volume of the cylinder is 256 pi over 9 centimeters cubed. So here's another example. Excuse me, a bit of a frog in my throat here. So PQRS is a rectangular field 155 meters long and 60 meters wide. And PQ, now this is a little blurred, but Q is the bottom right-hand corner of the rectangle. And I have a better, and R is the top right-hand corner. So PQ is a path, and the field has recently been plowed. So a woman can run at an average speed of 260 meters per minute along the path and 100 meters per minute on the field. She's starting off from P and she wants to reach R as quickly as possible. So she runs to some point U along the path, and then she runs from U to R. And so the question is, if the distance from U to Q is X meters, express what's PU and what's UR, and then find what's the time taken to reach R in terms of X, and then find the value of X for which the time is a minimum, and calculate this time in seconds. So here's the same diagram just to remind you all, and the question, and we can start doing some work and a slightly better quality picture there as well. So first of all, PU is equal to 155 minus X. And I just made a little note there. That's 260 meters a minute for PU. UR, using Pythagoras, is, so we can see that QR is 60 meters. So X squared plus 60 meters, sorry, X squared plus 60 squared, and get the square root of that. That is the distance for UR. And again, just made a note there, the UR piece is 100 meters per minute. So the time to traverse UR is, sorry, that there's a mistake there. The time to traverse, that should be PU. I'll fix this right now. be back in just 1 second. So we're saying that PU is 155 minus X and UR is X squared plus 60 squared, and get the square root of that. And so the time to traverse PU is 155 minus X all over 260, because speed or time is distance over speed. And the time to traverse UR is 1 over 100, the square root times 1 over 100 times the square root of 60 squared plus X squared. And so the total time T then is 155 minus X over 260 plus 1 over 100 times the square root of 60 squared plus X squared. And dt dx, that's equal to minus 1 over 260 plus 1 over 200 multiplied by 2x into x squared plus 60 squared to the power of minus 1 over 2. So let's break this out. We differentiate the first piece first. So 155 minus x over 260, when we differentiate that, we get minus 1 over 260. And the square root of 60 squared plus x squared, again using the chain rule and the power rule, we get that's 2x into x squared plus 60 squared to the power of minus 1 over half, and that's all divided by 1 over 200. And so moving on, so we have dt dx. We'll now move on to the next slide. So we have dt dx is equal to all of this, and so just to tidy it up a bit, I'm taking the 2x out of here, and so instead of and the 1 over 200, combining that with the 2x to just give us x over 100. And I'm also saying that dt dx is equal to 0. So x over 100 into x squared plus 60 squared to the power of minus a half, that has to be equal to 1 over 260. So you've got two terms here. You've the minus 1 260 piece, and that's added to the x over 100 piece. And so all I'm saying is that when dt dx is equal to 0, those two have to be equal. And so 260, so to simplify, to solve this, first thing I'm going to do is multiply across by 260. So that gives me 260x over 100 into x squared plus 60 squared, and that's all equal to 1. And then for my next step, I multiply everything across by the square root of x squared plus 60 squared. And so when I do that, 260x over 100 multiplied by x squared plus 60 squared to the minus a half. So when I multiply that by x squared plus 60 squared to the power of a half, I get 1. So on my left-hand side just becomes 260x over 100, and my right-hand side becomes the square root of x squared plus 60 squared. And so that becomes 260x over 100, sorry, that becomes 6.76 x squared is equal to x squared plus 3,600. Because 2.6 squared is equal to 6.76. Okay. And so we move the x squared across, and that gives us 5.76 x squared is equal to 3,600. And then we x squared then is equal to 3,600 over 5.76, and so x squared is 625, and so x is equal to 25 meters. And so moving on, remember we also need to find the time t, but we said that t is equal to 155 minus x over 260 plus 1/100th of the square root of 60 squared plus x squared. So, and we now know that x is equal to 25, and so we plug in the value of 25 and we get that t is equal to 1.15 minutes. Okay, let's move on. So here's some additional examples. So the distance traveled by an object is given by s is equal to 12t minus 2.4t squared, where s is in meters and t is the time in seconds. Find the speed of the object after 1.25 seconds and find how long it takes for the object to stop. So the speed is distance over time, or ds dt, and we said it's 12t minus 2.4t squared, so ds dt is equal to 12 minus 4.8t. And so when t is equal to 1.25, then ds dt becomes 6 meters per second squared, because it's 12 minus 4.8 multiplied by 1.25. That becomes 12 minus 6, and that's 6 meters per second. The object stops, the object stops, or is stopped, when ds dt is equal to 0. And so that occurs when 12 minus 4.8 t is equal to 0. And so that means that t is equal to 12 over 4.8. So it comes to a stop after 2.5 seconds. So another example then, the function f of x equals x minus 1 plus 1 over x minus 1. Explain why a line with the equation y is equal to 2x plus c cannot be a tangent to the graph of f of x. So f dash of x is equal to 1 minus 1 all over x minus 1 squared. So if f of x, so let's look at the x minus 1 piece first. When you differentiate that, you simply get 1. And the 1 over x minus 1, you use the quotient rule for that, and that gives you minus 1 over x minus 1 squared. So the slope of the line, so that's when you get f dash of x. And then separately, the slope of the line is equal to 2, because y is equal to 2x plus c. And so now we need to ask ourselves, why can f dash of x never be equal to 2? So x minus 1 to be squared is always positive. So 1 over x minus 1 to be squared is always positive also. So therefore, when given that f dash of x is equal to 1 minus 1 all over x minus 1 to be squared, that's always some number less than or equal to 1. And so because the slope is always of the curve is always less than or equal to 1, and the slope of the line is 2, the line cannot be a tangent anywhere to that particular function. And that concludes that. That's basically the answer. I came across this question when I was preparing for this, and it was in some old sample exam paper. And the question is simply differentiate with respect to x the natural log of e to the power of the natural log of e to the power of 2e. And so I'm going to let everyone think about that for a couple of seconds. And it would be interesting to see what answers you have. In fact, it might be fun if you want to type in an answer of what you think it is, and we can discuss it then in a couple of seconds. So first of all, this is not a function of x. This is a constant. And so when you differentiate that with respect to x, it's a one-line answer. If f of x is equal to this thing, then f dash of x is equal to 0. But has anyone any thoughts? Then I wonder on. We've answered the question, but I'm wondering what is it? Well, if we look, how can we simplify this? So let's break it down. So it's the natural log of e to the power of 2e. That is 2e by definition, because we had earlier the natural log of e to the power of p is always equal to p. So this simplifies to 2e, and then this piece here then becomes the natural log of e to the power of 2e, and so your answer is 2e. But that doesn't really answer the question. But well, doesn't answer the differentiation question, but it's a nice. I thought it was nice to get back into logs and exponentiation. That would be a nice little example to work through. Oh, I've done this again. Oh, sorry about this. This just machine has been fighting me all day. And I think, in fact, that we have reached the end. Yes, I just have one more slide. So here's just a couple of tips on the differentiation in general. Knowing how to do differentiation on its own is probably not enough. You'll have seen from the examples that you need kind of fluency. You need to be good at logs and indices and trigonometry and coordinate geometry and functions and limits. It is rare to see a differentiation question that doesn't require some of these. I'd encourage you to practice and revise regularly, because repetition is a great way to retain information. Flag the hard questions and do them twice. And also practice using your log tables. They really are vital for this part of the course. Try to get an in-depth understanding, and we've seen desmos.com, for example, which is very good. It's and there are other graphic calculator apps that you can get on your phone or your PC, and they can give an insight at times into how various functions behave, and they can be helpful to use to help you develop sketches and estimates where feasible, and so that you can ask yourself, did the answer match your estimate, and if not, then why not? There's many good math websites out there, and I would say Google is your friend for that. And in an exam, I would encourage you, obviously, manage your time. Take a few minutes to read the paper fully. At any given instant, try and maximize D marks dt. In other words, keep that slope of that curve as steep as you can. That means do the easy questions first. Do the ones that you're confident in. Get them done and out of the way. And try and present your work as clearly as you can, because when you are in an exam, you are communicating with the examiner. And so that is it. Thank you, and thank you for your patience with me. I had a couple of little problems with the PowerPoint there, and if you have any questions or feedback, do send it to info@ceia.ie and just mention differentiation in the title. Thank you all very much.
Okay, thank you very much, John, for a very nice presentation on differentiation. I've got one question just in right now from a student, and it's the question is, what types of careers involve differentiation? I'm not sure if would you have a good answer for that? So,
I think that as an engineer myself, I think that I do not use differentiation in my day-to-day work, but without an understanding of differentiation, there is a lot of engineering concepts that I wouldn't understand properly. I think it's a bit like in kind of simpler. If you have a calculator at home and it's got a square root button, you mightn't use the square root button very often, but it really is important to understand what the square root of a thing actually is. And I expect that well, I'm an electronic engineer myself. I expect that in chemical, in civil, in virtually any aspect of engineering, an understanding of differentiation and how functions behave is really important.
So with that, I would like to thank John again for a great presentation on differentiation. As always, just to recap a tiny little bit on what John has done. He's done an awful lot of work this morning. There's an awful lot covered. For sure, you need to use your log tables, the formula and tables booklet on page 25. There's a lot of derivatives there, and practice is key with calculus. And you can use the examinations, the exam papers, past papers, which you'll find at examinations.ie. And also, of course, the solutions and the marking schemes are available there. And as always, the Khan Academy is a very useful resource for testing yourself and finding out different ways of looking at things. Okay, so still no questions coming in. So we'll leave it at that for this week. So, and thank you once again, John. And so see you next week for the probability tutorial. Okay, so bye for now.
Bye, everyone.